It's a preliminary work. I will mainly provide some results that Maxime Caranzo and Nina have worked a lot on, trying to a new approach to do data assimilation with the ORCHIDEE land surface model. In the context and why it's in this session, I will explain just a bit before. We had in the past used mainly two different approaches. A gradient-based approach, we use the so-called BFGS algorithm, which has pros and cons. It's fast, it's deterministic, but it can get stuck to local minima, and the gradient is not easy to compute. We have used Monte Carlo approach in the form of a genetic algorithm. It's a global search, has a lot of features which are nice, but it's slow, and you don't easily get the posterior parameter uncertainty with that method. So what we wanted to test is a new, it's called history matching. It has been developed by UK in Exeter, Daniel Williamson, and basically it has been applied a lot yet to climate models, to optimize the climate model. We see some advantage, and it's an approach which is based on emulator, that's why we are in these sessions, and we see some potential advantage, especially to assimilate multi-data stream. I will try to explain what is history matching. So if you start on the left, you define a parameter set, so a few set of parameters. And in one wave, which is the first loop, what you will do, first you create an ensemble of one. Usually we make 10 times more times the number of parameters. With this ensemble run, then you have to run your model. You define then an emulator of that model for a specific set of metrics or scalar that you have defined, one emulator per scalar or matrix. And then with that emulator, you can really look with 1 million of tests of the model at all the space of your parameter space to possibly rule out or not rule out some part of the parameter space. And you use an implausibility measures. It's the distance between the model and the odds. And you try to be very conservative. You don't want to rule out too much space. And the emulator is based on Gaussian processes, which at the same time provide you not only the value, but the uncertainty. This is technically how it works. You have on the top, you recognize the ops minus the model in terms of variance. And you define this implausibility simply by having three terms. The middle one is the observation error, classical to the data assimilation that I've presented before. The model structural error, you assume also are normally distributed on the far right. And you have on the left, this variance, which is the emulator error that is provided by the Gaussian processes. So basically you want to have the minimum implausibility, and you set up a criteria if you want to rule out parameters that are above, and we usually take 3 sigma of that overall total variance at the denominator. So we exclude all parameters that are 3 times that total variance, and then we continue doing more waves iteratively to refine the emulator. So basically it's an emulator, different wave, you refine the search of your parameter space. Preliminary result, the context was published before. The gradient-based approach seems to be nice, but it's very sensitive to the prior parameter sets, and it can be trapped in a local minima. Here it was a comparison at FluxNet side that we did with the gradient-based algorithm and the genetic algorithm. I won't go into the details of that, but basically we always overperform with the genetic algorithm unless you do a lot of first guess started with the gradient base. So what we did an experiment. We started first at one site, Fontainebleau site, deciduous broadleaf forest, 11 parameter optimized for the ORCHIDEE model, pseudo data and real data experiment. Pseudo data, we created data with a set of parameters that we have randomly created. And we touch each time these 3 methods, BFGS, gradient-based, genetic, and history matching. History matching, the typical results that Daniel Williamson has played looks this graph. It's complicated. You won't understand maybe all, and I don't have all the time in 10 minutes. I just want to show you one thing, one little graph on the top, which is basically for the soil Q10 parameter and the VC max. This is a submatrices of the fraction of point with implausibility lower than the cutoff, which is the right bar. Gray means that all these values for combination of VC max and soil Q10 are implausible given the criteria of 3 sigma that we do. Whatever the other combination of parameters, you never can get have a decent fit with these Q10 value. So basically, it's shrinking your space, and the gray zone means you have shrunk all this space. And the rest, it's plausible. You don't have found, but it's plausible. And the lower graphics explain you a bit more on that. So this is typically how we do. And now if I compare the results from a pseudo data experiment, gradient based on the left, genetic algorithm in the central part, history matching on the right. You see, basically, you can see the fit to the observations. Of course, we don't see much the black, which is the observation, because this is a pseudo data experiment. So we should, in principle, have the green on the top of the black. We don't get that completely, and we see that the gradient base is the poorest in terms of RMSD, 0.38 compared to the genetic and the history matching with 25 waves. 25 waves, it's a lot of runs. It's 2,500 runs, so it's too much. We did that also with only 5 waves. Basically, I won't discuss too much how you can change the cutoff to restrict doing the waves, but you get an RMSD of 0.19, which is in between the gradient base and the genetic algorithm, but still with much lower run than the genetic algorithm. So I would say promising this history matching approach. If you look at the mean seasonal cycle in twin experiments, we are very close to the true one, but not quite exactly. We can't find the exact set parameters that we have used to create this data. Here, this is a complicated graph. On the y-axis, it is the number of runs each of these methods will need, and the NEE RMSE on the y-axis. So x-axis, number of runs. So you can really compare the method. The red BFGS, which is the gradient base, poor performance, but low number of runs. The blue, which are the genetic algorithm with either 32 or 64, seems to perform the best, but one of these history matching, the green one with 5, can perform better with respect to the number of runs in the first, depending on the criteria of how much you want to reduce the RMSD. But over time, the genetic algorithm continue to decrease. So this is really our first test of history matching. We think it's promising. If you look at the parameters, then it's a bit more chaotic, but it's very informative. This is the cross is the true parameters. The blue bar is the a priori value we started. If I start with BFGS, the gradient base, sometimes I see some parameters on the left where you have no sensitivity. It's difficult to calculate because we made a problem in calculating the gradient for senescence temperature. And for VC max and LAI max, we have we are on the edge. We have an anti-correlation, and it was falling, trapping in a local minima. If I look at the genetic algorithm, it's where only a few parameters circled here are a bit further from the cross. While the history matching, we have a few more parameters that deviate from the true parameters, still providing a relatively good match. So what we say, there's many different combinations. It's a difficult problem to optimize parameters. We did similar experiments, but with real data. So here, real data at Fontainebleau, it's always good to check with that. With 25 waves of the history matching, we have an RMSD of 1.39, which is in between the gradient base with 15 iterations and the genetic algorithm with 50 iterations. But so basically, we are not as good as the genetic algorithm with the history matching, but if you take 5 waves, which is only 500 runs, we are decent compared in between the genetic algorithm and the gradient. So my take-home message, so we are exploring that, and I think there's a lot of potential of this history matching. Sorry, I went fast. So we can look here at, in these real data experiments, this typical graph where you see on the upper triangle, the gray zones that tells you, oh, these parameters 2 by 2 cannot be combinations that match your data. But at the end, what you get is not one point. Here, what I've shown you when I show you here the output is just we took from the history matching the point that was providing the smallest LMSD, the smallest cost function with this smallest implausibility that I've shown you at the top. So basically, it's very, I think it's promising. You have this ensemble, you have reduced your parameter space with an ensemble that you can use to characterize the uncertainty from the history matching approaches. And also, we see here that there is, at the end, 0.70% of the whole space that is plausible, that still is plausible. So it's quite a strong reduction of the initial full space of parameters. So my conclusion, history matching is a promising approach. Exploration of parameter space is an ensemble of plausible parameter vector. So I think it's a nice way to valorize emulator, and I think it will be more powerful with global simulation, especially coupling with atmospheric transport. It has been applied mainly to climate models, and I cite 2 articles here with the LMDZ climate model, but also tested with joules in the Baker et al. Paper. It's a very nice paper. They were the first to test that, I think, with the joules land surface models. I really encourage people to read that. And the next step for us is to continue with the stage and the internship and to use it as to test as a multi-site optimization with global, also with global run, global optimization with different data streams. And I think we want to compare with other approaches like ensemble, Fordivar ensemble, that you, Tristan, have also been used. And so we would like to still compare with different approaches. So thanks. I hope I'm in time.